So it's very special also because I don't come from the physics community. In fact, last time I studied physics was God knows how many years ago, in class 12. So I am by training a statistician and by profession a probabilist. But yet I'm enjoying a lot many of these talks because they relate to probability a lot, and I'm learning a lot of new things too. Okay, so let's see how much related stuff I can tell you. So this is a joint work with my PhD student Noyan Bhattacharya, who's a very good hardworking PhD student at ISI, and my colleague Rajat Shubha Hajra. So what is a branching random? So as you can see, there are three phrases, and I'm going to talk about what is the first one, what is the second one. Third one just essentially means power law distribution. It's a little bit different than that, but honestly speaking, it's power law. I'll tell you what's the difference later. So what is a branching random walk? So a branching random walk is, roughly speaking, it's a collection of points or particles that are starting from a single particle, branch and then spread. That's the idea. It's a very toy model. There's no interaction between the particles, and then they can cross each other without colliding. So I'll give a better description than this. The question that we are going to address in this talk is what is the long-run configuration of the positions of the particles? And this model was introduced back in the 70s by Biggins based on two other works here. Okay, so what is the description? You start so we are thinking of time as epoch, so discrete time. So generation 0 starts with one particle at origin. Okay? Then the particle branches into a random number of, which involves at least one, for this talk I'll make an extra assumption, new particles. Each of these new particles, what they do is they undergo a random displacement having a power law. So that's where the power law comes in. So that's regular variation. In general, in the model, the power law assumption is not there, but in this room, I see that power law comes naturally in many things, so I don't really have to introduce what it is and why it comes. So we just assume that the displacement is a power law. Okay, so this gives rise to generation 1. Then what happens is, one assumption that we are making is all these displacements, let's assume they are positive. So I'm only allowing particles to move to the right direction, on the real line. And they're independent of the branching mechanism. So it doesn't depend on how many particles there came and so on, and it's in the first generation. And then the displacements of the offspring particles coming from different parents are independent. So this doesn't really make sense right now, but now it will make sense. Each particle in generation 1 will undergo the same kind of random mechanism independently of each other, which means each of them will branch, and then each of them which will make some displacement. And this will give rise to generation 2, subject to this thing. Displacements coming from the different offspring particles coming from different parents are going to be independent. And again, as I said, I want to stress that there is no interaction between the particles, and this dynamics is going to go on. So here is a pictorial description. So this is the generation 0. In generation 1, what happens is there are two particles. So this branches into two particles and they make some displacement. This is the first, say this is the first particle, this is the displacement. Second particle, this is the displacement. So this is a view of the same thing. It's a snapshot at generation 1, this is a snapshot at generation 0, this is generation 1. Then the snapshot at generation 2 looks like this. This, say, branches into two. Each of them makes some displacement. This is the displacement of this guy, for example. And here, this one makes, it branches into 3 and makes some displacement. Now, the point is, all of these guys here, which are coming from the same parent, these displacements are independent of these displacements. And they're also independent of the number of particles, of the branching mechanism, I should say, the number of particles that they're born. The only thing that can be dependent is all the red ones here and all the blue ones here and both the blue-green ones here. That's right. Okay, so any question on the model at least? Okay, so I'll move on to why is it important quickly. So they come from different contexts, and especially the power law displacements, I think is naturally arise in ecology. Levy flights, that's a key phrase I've been told. I'm not going to talk too much about it, but it basically gives how a growing population invades a new environment. And our model is we are only going to allow particles move along a single ray, okay, without any interaction, of course. And more complicated models can be whether the particles can be in a plane or in a box and so on. It will be 2 or 3 dimensional versions of this. Okay, so for this talk, we are going to restrict only this simple model, and we are going to study the long run configuration of the particles. So let's see what do I mean by that. So this is the goal, roughly speaking. So what we want is we want to obtain the limit as n goes to infinity. Here n will denote the epoch or the generation. So Nn is what? It's a random point configuration consisting of the properly normalized positions of the particles coming from the nth generation. So if you go on running this, I showed you the snapshot up to the second generation, but if I ran it up to nth generation, I'll see a lot of particles at various points. Of course, the particles have a drift towards the right side on the average. So therefore, you would see that in the long run, it will go to infinity at some rate. So you need to somehow normalize it. Once you normalize it, where does it go in the limit? That's the question that we are trying to answer. Okay, I'm going to be still vague about properly normalized. I'll make it more precise later. Now, once I can do that, why is it important? If I can somehow find the long run configuration, then I can find long run, this is like a black box, which can be used to compute the long run behavior of a lot of quantities, like the position of the rightmost particle coming from the nth generation. That, of course, will go to infinity, but at what rate? After scaling, what will it go to, and so on. This is a random quantity, because displacements are random. So everything is random here. So we're talking about convergence and distribution. Also gap statistics. So if you look at the kth maximum, kth rightmost point, at the k minus 1th rightmost point, what is the distance? How does it scale, and where does it go, and so on. All of this can be computed once we compute the limit of this, at least theoretically, using what is known as continuous mapping here. I'm not going to go into the technicalities. So these were the two predictions, and this is where the connections to statistical physics comes in, by Eric Brunet and Bernard Derrida in a paper in journal StatPhysics. They considered as actually 4 models of branching random walk and actually branching Brownian motion, which is a continuum version of this thing, where particles are not just making displacement, they're doing a Brownian motion. Each of them, after branching, making a Brownian motion, roughly speaking. So they predicted that the limiting configuration is what is known as a decorated Poisson point process. Essentially a Poisson mixture of same kind of point process independent copies of, roughly speaking. So what exactly I mean, I'm not going to tell you. Again, they also said that the limiting configuration should exhibit what is known as property of superposability. Now, what exactly that means, I'll come to that later in the talk. And they also asked the following question. They asked whether these two are actually equivalent or not. It turned out they are actually. It was a work of Pascal Maillard. Is the pronunciation correct? I don't know. Anyway, these two are actually equivalent. Anyway, so some of the existing works, this model is very important in probability theory at least, because it relates to various other things, free fields, fast passage percolation, free polymers, multiplicative chaos, various things. Some of the recent works which if these connections are written there. And the Brunet-Derrida predictions were actually proved mathematically for branching Brownian motion by 2 groups of people. One is this group, I would say this is mostly, well, this was led by Anton Bouvier, so I'll say German group, and I'll call this the French group. And for branching random walk, this was verified by Madoule in 2011, but the paper got accepted very recently in Journal of Theoretical Probability. That just shows how long it takes for math papers to get accepted finally. Anyway, so the order and gap statistics for critical branching, Brownian motion were studied by Kabir Ramola, Satya Majumdar, and Gregory Say, for example. And then, heavy tail context, heavy tail displacement is also not that new. Rick Duret actually studied it back in 79, 83, and there are some more recent work. There are some few more recent works. So that made us think, okay, why don't we try to verify the Brunet-Derrida predictions, at least in this case, in the heavy tail case. So that led us to this work. So what are the assumptions? The assumptions are the following. We assume that the mean number of offspring particles at every generation coming from one parent is something bigger than 1. So in other words, we have a subcritical regime. So the underlying branching process is subcritical. That's what I'm assuming. Also, I'm assuming that every particle produces at least 1 offspring. Honestly speaking, this is not so important, because if it's not there, this is just to make sure that this system survives with probability 1. Otherwise, I just have to condition on the survival. So I'm not doing that, so making it easy. So I also need another technical condition called Kestenstiegum condition, which is slightly more than the first moment should exist, should be fine. Okay, so our assumption in this model, special assumption is that the power law decay holds. So the displacement bigger than x is constant times x power minus alpha for large x. CR alpha are positive constants. And displacements of offspring coming from the same parent follow some kind of joint power law introduced by these three people. These are different Roy, Joyjit Roy, it's a different Roy. So Linskog, Resnick, and Roy. So roughly speaking, this assumption tells you that there are a lot of big displacements on the average. So on the other word, for example, if you compare with Gaussian, this is much bigger. So in Gaussian case, the displacement would be big with a very smaller probability compared to this one. So you'll see a lot of bigger displacements. That's the model. Okay, so what are the results? So the results are the following. So essentially what you have to do is you have to look at the point configuration of points coming from the nth generation. You have to divide it by mu power n over alpha. This comes from the scaling that Duret got in his work, because the rightmost particle is growing like that, exponentially. So the result is, as n goes to infinity, it is nn, this is the configuration, divided, you look at the position of the nth generation divided by mu power n over alpha. This converges indeed to a decorated Poisson point configuration, and this satisfies superposability. So Brunet-Derrida, the predictions are indeed verified. And initially we did it for the independent case, in the sense that we assume that all the displacements are IID with a power law. And then two people, my colleague Antar Bandyopadhyay from ISI Delhi and Joe Bartho from France, actually he's in ETH, University of Zurich, right? University of Zurich, he visited us, he also asked this question. They asked this question independently to my student. So this answered this question. Now, what is superposability? I'm not going to talk too much about it. It just says that, roughly speaking, superposability means the following. You take two independent copies of the point process, of the limiting point process. You multiply one by A1, in the sense that multiply all the points of one by A1, another by A2, superpose these two. If this condition is satisfied, then this new point process that you get, point configuration that you get, has the same distribution as the original one. So this is superposability. In the following sense, it's superposable. And this was actually introduced by these three people, but this was sort of esoteric in literature somehow. So summary is the following. So we have computed n star, as opposed to light-tailed case, this is a much explicit description. As a result, in the independent case, we have a lot of results. And we have answered a question asked by Gregory Scher to my student in a conference, and also some other questions too. And we have improved the result of Duret, the dependent displacement case. And most of these results are not as explicit as this one in the light case. So sorry, I'd like to stop.
Time for questions.
Yeah.
Superposability hold when you introduce an annihilation rate of particles?
I don't know. That's a good question. My guess is it may, because the superposability is coming because after some, essentially it's because you're adding you're actually superposing some point process at some level in the limit. So as long as that structure is there, my guess is that it will still be superposable. This property, stability or superposability, whatever you call it. But that's a question that we haven't looked at.
If there are no further